Hello and welcome back. In this lesson, we are going to look at inner products or dot products. And we have been using this quite a bit in the previous videos. Here we'll do a slight deep dive into what it means and how it can be useful. So, inner product essentially takes two vectors or two functions and then returns a scalar value. So, if we have a vector and if we have two such vectors and if we do the dot product or inner product, then what we get in output is a scalar value. So, this could be vectors, or if we have two functions and we do a dot product, what we get in the output is a scalar value. What I mean by scalar value is just a number. For example, if we have a vector x1 that is 1 1 1, it just has 3 ones in it, and then we have another vector which is y, and this vector has values 2 2 2. For simplicity, let's say that this is just x instead of x1. Now, if we want to perform a dot product between these two vectors, we would have to flip this, because right now this is of shape 3 by 1, this is of shape 3 by 1. And if you remember, we need that these values should be the same. So if we flip x to x transpose, then what we create is this vector, which has a shape of 1 by 3, 1 row and 3 columns, and that matches. So now it matches with the value that y has, which is 3 by 1. And so to perform our dot product, we would, our inner product, we take this vector x transpose, take the second vector y, and then we multiply each value with the other value. So the first thing we would do here is take this 1 and multiply it with the 2. Then we take the value of this one, multiply it with the 2 below it, and so on we go until we are out of the numbers here. And so this one we multiplied with this 2, and then we add all of them together. So what we get in the end is this 1 times 2, that's that one. Then we have a plus 1 times 2, that's the second one. And finally we have the 1 times 2, that's the last one. And so if we add all of these up, what we get is 2 plus 2 plus 2, that is equal to 6. And so the dot product of, or inner product of x and y is 6. Now along with this notion, there is a rule or a property that inner products must satisfy, and one of them we just talked about is as follows. It says that x, if we dot x with y, which can be written as x comma y in parentheses or x comma y in angle brackets, this needs to be equal to y dot product of y with x. What it means is, instead of transposing x that we have here, what happens if we transpose y? If we transpose y, we have 2 2 2, and now if we dot that with the value of x, so x here remains as 1 1 1. Again, if we look at the shapes, we have this is 1 by 3, this is 3 by 1, and so dot product is possible. So let's go ahead and do that. We have 2 2 2, and this is 1 1 1. Again, if we look at the multiplication, we take this 2, multiply it with this one, take this 2, multiply with this one, take this 2, multiply it with this one, and so what we have is 1 times 2 plus 1 times 2, or the other way around, 2 times 1 plus 2 times 1, and so on. So this is 2 times 1 plus 2 times 1 plus 2 times 1, and so that again gets us a value of 6. So these two values are same, and so we say that this rule is satisfied here. And the next rule that that the inner products or dot products need to satisfy is that a x1 plus b x2 dotted with y is the same thing as a, which is a scalar value, which is multiplied with the dot product of x1 y, and b again a scalar value multiplied to the dot product of x2 and y. So let's for instance say that our x1 is simply 1 1 1, our x2 is simply 2 2 2, and our y, let's say that is just 3 3 3. And for a, let's say the value of a is uh, 2, and the value of b is let's say it happens to be 3. Now we perform these calculations that we said above should be true. So first we calculate a, multiply a with x1, and then again multiply b with x2, and then add those two together. So here is what we get. So we take the 2 multiplied with 1 1 1, then add that to 3 multiplied with the 2 2 2, and so what we get is this is 2, so we have 2 2 2 plus this becomes 6 6 6, and so 2 plus 6 is 8, and so we get output vector which is just 8 8 8. And then we say that we are going to dot that with y, and so to dot it with y we of course would have to perform the transpose, and so let's say we transpose it and put it as a row vector 8 8 8, and then we dot that with y, which is 3 3 3. And now when we perform the dot product same way as we did before, it's 8 times 3 plus 8 times 3 plus 8 times 3, and so that essentially is 24 plus 24 plus 24, and that gets us a final value of 4 plus 4 is 8, 8 plus 4 is 12, 1, and so this is 6 plus 1 7, so we get a value of 72 on the left hand side. Now to for this property of inner product, what we need, it needs to equal this side. So what we are saying here is we take the 2 and multiply it with the dot product of x1 and y. So why don't we first get the dot product of x1 and y? So to do that we would simply type x1 comma y is equal to, and here we again would have to transpose x1, so we just say 1 1 1, and the y is 3 3 3, and so what we get here in the output is a scalar value. So this is going to be 3 plus 3 plus 3 plus 3, which is 6 plus 3 is 9, and then we multiply a with this dot product that we just got, and the value of a is 2, so we multiply 2 with 9, and so what we get in the output is 18. So that's this part 1 we did just now. Next is part 2, where we first take the dot product of x2 with y. So this time our x2 is 2 2 2, so we take the transpose of that and put that right here, 2 2 2, and then we take the values for y, which is simply going to be 3 3 and 3, and 2 times 3 is 6, so 6 plus 6 is 12 plus 6 is 18, and we just say that that's 18, and now we multiply the dot product of x2 and y with b, and as we see above, the value of b here is 3, and so we take the 3 multiply it with 18, and so what we get in the output is 8 times 3 is 24, 2 carry on, and so we have this as 54. Finally, if we add these two values, so if we add the 18 with 54, let's see what we get. So 18 plus 54 is 8 plus 4 is 12, we carry on 1 here, so 6 plus 1 is 7, we get a value of 72, and as you can see that both these values are the same. So that is to say that this relation that we just wrote above does hold, and it is true. So this was the second one we looked at. The first one we looked at was this one, and so both of these are true. And the last property that we are going to look at is positive definiteness. So what I mean by that is, let's say if we have value for x and we have values for y, so vector x dotted with x needs to be greater than equal to 0, and x, the dot product of x with x can be 0 only when x is a 0 vector. So this is true only when x is a 0 vector, and we talked about 0 vectors in one of the previous videos. So a 0 vector or a 0 function, and we can look at an example. So let's say we pick the example where we have x which has value of 1, 2 and 3, and now if we dot this with x itself, we would have to transpose one of them. So let's transpose x and then dot that with x. So we have a row vector of 1, 2 and 3, and we are going to dot that with a column vector of 1, 2 and 3, and so in the output what we get is simply 1 times 1 which is 1, plus 2 times 2 which is 4, and then we have 3 times 3 which is 9, and so if we add this we get a value of 14, and again 14 is greater than 0, and so this property that we said here does hold. If we just had values as 1 1 1, we would have gotten 1 plus 1 plus 1 which is 3, again greater than 0. So the names that we would call these or the formal um, properties that we are going to call this as are the following. So the first one is this one where we say symmetry. So this is all about symmetry, and we say that swapping the two inputs does not change the result. And the second one is linearity in the first argument. So this one right here, linearity. So linearity in the first argument, that is scaling and adding the vectors, behaves nicely with the inner product. So linearity in first argument. I apologize for this lag as I'm writing. And this last method we looked at is positive definiteness. And here we are simply saying that this has to be true. So those are the three main properties, and we already looked at some of the examples. What we'll do now is move on and look into some of the use cases of these dot products or standard inner products. Let's say we can formalize this by saying that if we have a vector x which has the values x1, x2, x3, and so on up to xn. We have a vector y which has values y1, y2, y3 all the way up to yn. Then their standard inner product would be x transpose dot y, which is going to be x1 times y1 plus x2 times y2 plus dot 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 xn times yn, and we can compute this manually. We already looked at this, but this is just another example. Let's say we have a vector which is 2 minus 1 3, and we have vector y which is 4, 0 and -2. We can perform the dot product of x transpose y, which is going to be 2, -1, 3, dotted with 4, 0, -2, and that would give us the following. 2 times 4 is 8, plus -1 times 0 is 0, plus 3 times -2 is -6, and so the output we get is 8 minus 6, which is 2. And so the value for x transpose of y, x transpose dot y is 2. Now this is the standard manual calculation that we just saw. We can use this calculation to in the real context of neural networks and see how it can help us. It can help us calculate something called as the norm and angle, and we'll look at this in the next video in further detail, but here is just a quick look at it. Let's say we norm is essentially the magnitude of the vector. So if we have a vector, we simply try and calculate its length. And so if we have this vector, something like this, which is going here up to 2, and this is 1, then what we are looking at is a right angle triangle, and this is the hypotenuse, and the length of the hypotenuse, as you may already know, is nothing but square root of the length, squared length of this side, which is 2, so 2 squared, plus squared length of this side, which is 1 squared, and so that is square root of 4 plus 1, which is 5, so square root of 5. And that's the magnitude of this vector, which can be given here by the coordinates of this point, which is x-axis 2, y-axis 1. So that's the magnitude of this vector x. And here we can uh, look at the notation. We type two parallel lines, then type write x, again two parallel lines, and then write 2 here. So that's the squared norm, and this is nothing but x transpose of x. So here if we say that our x value is 2 comma or 2 1, so if this is the vector we have x, then if we perform this operation where we get the uh, transpose of that 2 1, dot that with 2 1 as a column vector, then we have 2 times 2 plus 1 times 1, we get 4 plus 1, which is equal to 5, and that is the squared norm. And so if we take just x without the square, this would be square root of 5, and that is exactly what we talked about earlier. And so that's one useful thing, because if we now do the same thing with y, we can use it to find the cosine of an angle, and that's the interesting part. So let's say we have y, and for this y, let's say we have a vector y which has values maybe 2. Let's say y, we can draw it somewhere here, and let's say this goes up here, and maybe if I can pull that graph down a little bit, so take this, pull it, and oh, maybe not, maybe I can just move this page down. So let's say if we are right here, we have 2, and our vector y happens to be on here, which is this is 1. Let's say we are at 1 comma 2, so the other way, 1 comma 2. So our y is 1 2 vector. Again, if we take the dot product of these, we have 1 2 and then 2, sorry, 1 2 again as a column vector, and this 1 times 1 is 1, and again 2 times 2 is 4, so we again get the same value of square root of 5. And if we take just the norm without the square, then so this would be 5, and then without the norm, without the square, it would be square root of 5. So this would simply be 5, and if we take the square out, then we have the square root of 5. Now with this, what we can do is calculate the cosine of an angle between these two. So cosine of an angle, and that is an important property that tells us how uh, the direction and how close or far they are from the weight vector in neural networks. So we can say cos of theta is equal to the dot product of x and y divided by the the magnitude of x vector x multiplied by the magnitude of vector y, and we can get the dot product of x and y right here. The x vector is 2 1 and the y vector is 1 2. So the dot product would be 2 times 1 is 2 plus 2 times 1 times 2 is 2, and so we get a value of 4. So this is 4 divided by square root of 5 times square root of 5, which is equal to 4 divided by 5, and that is equal to 0.8. And that is that can get us, so if we get the, to get the theta, we would simply do arc cos of 0.8, and let me look into the calculator to get that value, and that value is 36.86 degrees. And so what this tells us is that if we look at these two vectors, this x and then this y, this particular angle in between them is 36.86 degrees. And so that is a really interesting property, because if we had another vector, let's say we had another vector which was something like this, maybe value of -1 plus 2, right? -1 plus 2. Let's see what happens if we have that. Let's say the value, the vector y we had was for some reason equal to -1 for x and 2 for y. If we now dot x transpose y, what we would get is 2 1 dotted with -1 2, and this would be 2 times -1 is -2 plus 1 times 2 is 2. We get a value of 0, and if we put this information in this formula right here, what we get is cos theta is equal to 0 divided by square root of 5, which is for x, and the norm of y would still stay the same, or the magnitude of vector y would still stay the same, because we would square that value for -1, and then we would square the value for 2. That still equals 1 plus 4, which is square root of 5. And so we still have the square root of 5, but look what happens here. We get in the output is 0, and if we try and get the cos inverse of 0, what we get is, I think, the angle of 90. So if I take cos inverse of 0, that is theta is approximately equal to arc cos of 0, that gets a value of 90 degrees. And what that says is, if we try and look at the new vector that we just created, which was this vector right here, then this angle that it makes with the x, which is this one, is 90 degrees. And that is to say that this vector y is orthogonal orthogonal to the vector x. And as you remember, when we looked at decision boundaries, usually we would have this uh, vector w, which would always be orthogonal to our decision boundary, which we see here. So this would always be orthogonal. And that's sort of the relation we calculate when we do W transpose P plus B. So that's the inner product we do here, which essentially helps us get that orthogonality, and that's what we just saw right here. Let's now look at the inner product of functions. The inner product of functions, and the inner product of functions is given by integral. So if we have two functions, which is f, let's say one function is f, other function is g, then the inner product of this function, these two functions, continuous between 0 and 1, would be f of t, integral of f of t times integral of g of t dt. And the conditions that this needs to satisfy again are symmetry. What this means is integral of f of t g of t dt is this needs to be equal to the integral of g of t times f of t dt. Next is linearity, which is to say that integral of a f1 plus b f2 times g is equal to the integral of a, so the a times integral of f1g plus b integral of f2g. And so I'm just going to omit that here. And then last one is positive definiteness. What this means is if we take the function f, and if we perform integral of f and square that, its value should be greater than or equal to 0. And if this squared value of ft squared dt, if that is equal to 0, then we say that f is continuous, and ft square is continuous and non-negative. So it must be 0 everywhere on this range 0 to 1. And so this has to be a 0 function. If we try to look at some examples, let's try to do that now. Let's say we have a function f of t that is equal to just t, and we have another function g of t which is t squared, and we are going to look at this on the range 0 to 1. So if we first compute uh, uh, let's first perform this inner product of these two functions f and g, which is going to be equal to integral 0 to 1 t multiplied by t squared, and this is dt. So this calculates out to integral of t cube dt, and we compute the integral. What we get is 1 by 4 times t raised to power 4, and this values go from 0 to 1, And so what we do then is substitute the values. So we say 1 by 4, and the first value we get for t is 1, raise that to the power 4, minus 1 by 4, we take the value of 0 and raise that to the power 4. So essentially what we are saying here is this is going to be just 1 by 4 minus 0, and so this stays as 1 by 4. And as we can see that this dot product of two functions is 1 by 4. Now we can also get the norms of these, so we can say that this is the squared norm of t, which is equal to 0 to 1, and this is t squared dt. So we are talking about the function, and the integral of this would be 1 by 3 t cube, and this goes again from 0 to 1. We substitute the values and you'll see that this comes out to 1 by 3, and if we remove the square, we just take the magnitude. This would be square root of 1 by 3. Likewise, if we take the value of t squared and get the magnitude of that, we would say integral 0 to 1, that's t squared, and square of that dt, and that essentially would be t integral of 0 to 1 t raised to power 4 dt. And if we uh, look at get that out of the integral, we would have 1 by 5 into t raised to power 5, that goes from 0 to 1, and so that would be uh, just 1 by 5. And if we now try to get the uh, the magnitude, would be simply square root of 1 by 5. Now this again can be used to find the cosine between the vectors, function vectors there that we have, f and g. So we can say cos of theta is equal to the dot product between these two functions, which is the integral we just did, and then the magnitude of each of these functions, which we have calculated above. So this is 1 by 4 divided by square root of 1 by 3 multiplied by square root of 1 by 5. So that is essentially 1 by 4 times square root of 15, and this comes out to 0.9682. And if we try to calculate the theta arc cos 0.9682, and let's see how much that is. I think that's around 14. Let me check. So I'm opening the calculator, and here I have the cos, arc cos, that I'm trying to calculate. That comes out to arc cos of 0.9682 is 14.848. So this is around 14.48 degrees. And so what this is saying is it's a small angle, and so the functions t and t square are fairly aligned. Now let's look at an example of orthogonal functions. So let's say orthogonal functions, and here again we have two orthogonal functions on 0 and 1. Let's say h of t, that is t minus 1 by 2, and the other one is just constant 1. So if we perform inner product of h and 1, which is just a constant, this would be 0 to 1 t minus 1 by 2 times 1 dt, that equals 0 to 1. this is t dt minus 1 by 2 integral 0 to 1 1 dt, and if we keep solving this, this becomes this first part would become 1 by 2 t squared, and this is from 0 to 1, and the second part would be simply just minus 1 by 2, this would be just 1, and so that's t, and that's 1 minus 0. So to be correct, that's just going to be t, it goes from 0 to 1, and if we plug in the values, we have 1 by t times 1 minus 0 minus 1 by 2 into t, which is going to be 1 minus 0, and we have 1 by 2 minus 1 by 2, which is equal to 0. And so what this tells us is that the h is orthogonal to the constant 1, and this again is the same idea that we talked earlier. If we wanted to get the squared values of the norm, we could say h and then squared is equal to integral 0 to 1 t minus 1 by 2 squared dt, and if we solve this, we get 0 to 1. This is t. Let me write that clearly. This would be t square minus t plus 1 by 4 dt, and we continue integrating this. So this becomes, the first part will become integral 0 to 1, so t square dt minus integral 0 to 1 t dt plus 1 by 4 integral 0 to 1 dt, and this becomes 1 by 3 t cube 0 to 1 minus, this becomes, the second part is going to be 1 by 2 t square, again 0 to 1 minus 1 by 4 t, again 0 to 1, and this would be 1 by 3 1 cube minus and that's going to be 1 by 3 z 0 cube, and that second part would be 0, so I won't write that again here. So this is going to be t squared, so that's essentially 1 square minus 0 minus 1 by 4 1 minus 0, and so what we get in the end is 1 by 3 minus 1 by 2 minus 1 by 4, and so this is, let's see, this is minus t, so that's minus, this should have been plus, my mistake, so that is plus, and if we try to calculate this the decimals from this, let's see what we get. 1 by 3 is, so let me write that down right here on my calculator. 1 by 3, 1 divided by 3, that's 0.33, so this is 0.33 minus 0.5, and this is plus 0.25, so if we add these, 0.33 minus 0.5 plus 0.25, we get 0.08, and so that's the value of h squared. So that is the norm of h. So norm of h, and if we try to get just the value of h, that square root of 0.08, that would be simply the magnitude of the vector function h that we have. And to get the value of that, let's try and get that as well. So what we have, 0.08, and to get a square root of that, we simply do square root 0.08 and we get 0.2828. So that's the intuition behind the vector functions, and earlier we looked at the regular column or row vectors. So in summary, if we think conceptually what dot product is actually doing, so what it is doing is, if we have, let's say from neural network standpoint, we have, let's say, a vector x with some values in it, and then we have the weight vector w with some values for the weights in it. Now when we perform the operation of w transpose x, we are doing this linear combination of the w's with the x all the way up to the nth w and the nth x that we have. So if the w and x, if these two vectors point in the same direction, if w and x are pointing in the same direction, then the output of w transpose x is a large and it's a positive value. If the w and x, they are in opposite direction, then this inner product or dot product, uh, it can be large, but then it would be negative. That is to say that they are pointing in different directions. And for if we perform this particular operation, and if we see that this w and this x, if this comes out to be 0, then this tells us that the vectors are perpendicular to each other. And as we have seen previously, if we look at the neuron output, we know that that is given by w, that is given by n, based on the notation that we have been using. N is equal to w transpose p plus b, b for bias, and then there is an activation function that gives the value of a, which takes in the neuronal output, or that essentially this is the neuron output, that's the input to the transfer function, which is n. So every neuron in this case is computing a dot product between the input and its weight vector. So why is this important? This is important because it, in a way, it works as a similarity detector. It works as a similarity detector. So each weight vector w represents like a pattern. So w, we can think of it as some pattern that we have, or could draw it with a different color. So we have this w vector, which maybe is some specific pattern like this, and then the input that we have, uh, uh, input, if it's a similar pattern, maybe we get a larger values for the dot product. So for example, if we have w which is 1 1, so that's a diagonal pattern that goes up like this, and we have a value of p which is 0.9, 0.8 positive, somewhere close to that, then we see that if we perform a dot product w transpose p, it would be around 1.7, and this is again a similar direction, it's positive and it's a high value. So we see that they are pointing in the same direction, as opposed to p vector, which is minus 0.9 and 0.8, which if we try and calculate the dot product now, it is going to be minus 0.1, and this dot product is again negative and it is a small value. So that tells us that this vector p in this case is not similar to w. So neurons act as pattern matchers, and they do so by using dot products. So that's one intuition there. The second intuition is that when we look at the dot product as projection, so the dot product between W transpose and P is equal to the magnitude of W times the magnitude of P times the cosine of angle between the two. And so this is the projection of P. So if we have some vector P, that is the projection of that vector onto the vector W, as we see here. And this is the projection, that's what we have. This is the W transpose of P. And what this gives us, this sort of quantifies how similar the vectors P and W are. In other words, each neuron is projecting the input onto this preferred direction of the weight matrix, and then we have the decision boundary which we add to this, that sort of moves the decision boundary. So if we look at some concrete examples, let's say we have a weight vector that is, I'm going to write here, weight vector that is 1 1, and we have a bias of -3. Now if we calculate the A, let's look at just the sign of what your value we get for this linear combination, which is W transpose P plus B, and here let's say the values we are going to look at in this example, because this is 1 1, weights are 1, this is simply going to be 1 times x. So what I mean by that is, we say sine, and we have this vector 1 1, then we have the x1 x2 s2 inputs, we add the bias term to this, which is -3. So essentially what we are looking at is sine of this is x1 plus x2 minus 3. And if we now try to put some values in this, so let's say we have the point 4 1. If we try and calculate the value for W transpose P, just that dot product that we have, it's going to be x1 plus x2. So let's say this is x1, this is x2, that's what we have. So the dot product will be just 5. Now if we calculate the entire thing, which is add the bias to it, bias is -3, so 5 minus 3 becomes 2, and that can help us determine the class. The sign is positive, so this belongs to class 1. If we try to use a second point, let's say 1 1, the dot product of this would be 2, subtract the bias from it, we get value of -1, so the class is negative. And likewise, let's say have another point 2 2, the dot product would be 4, or inner product would be 4, and we subtract the bias -3 from this, we get value of 1. This is positive, so this belongs to class 1. And let's say we have a point 0.03, this lies on the decision boundary, and so here the dot product would simply be 3, and if you subtract the bias from it, we get a value of 0, which means that this lies on the decision boundary itself. So what do we understand from this? What we get is that this part right here, that's what we were talking about. This is the projection, right? Projection. So projection helps us sort of get the magnitude of the pattern that is matched, right? The pattern that's in W, that we are trying to get a pattern that's in W and the pattern that's in P. So if the points with projections, so projections is greater than 3, then they usually are going to class 1. If the points and the projection, if the projection is less than 3, then we say that less than 3 in this case, which here in this case was 2. So this one we said that that went to the negative class. So that's sort of the intuition behind it, and if you try to plot this on a plot, you'll get a clear idea as to how this works. So in the end, then what the dot product helps us do. So dot product or the inner product helps us project input. So project the input P onto the weight, the direction, weight direction that we have, and that's and when we talk about projection, a very simple intuition about this is think of shining a light. So if we have some light here, if we shine the light on this point P, then the shadow that this would create on this particular W, that's your projection. So that's this particular part is the projection created by this line, the light up top, that point. The next point is bias, and as we talked about, bias simply helps us move the decision boundary. So it sort of shifts the decision threshold, and it finds best place where it can sort of separate the classes. And the decision boundary then, which we have discussed extensively in one of the previous videos, is so all points with the same projection equals minus b. So all points in the same projection. So line or plane that's perpendicular to W. So as we saw here, where if the projection is greater than 3, then all of them are in positive class. If the projection is less than 3, then they are in the negative class. So B is minus 3. So if you look at minus B, that's going to be plus 3. So this is essentially saying minus B right here. And then the classification is just comparing the projected value through a threshold. So all neural networks are then doing is taking the inner product of the inputs with the weight matrix and then adding bias to it to find the appropriate decision boundary to help in classification task. That was it for this video. I hope in this video you got some intuition about what is inner product, how to think about an inner product, and how it helps in finding, how it helps neural network to find decision boundary. Now before we end this, just a very quick note on the similarity, and often this can be confusing. So what I said was, if the dot product between two vectors is large, so let's say if we have W that is 1 1, and if we have a vector P1 that is 4 1, right, and we have another vector P2 that is 1 1, if I plot this on here, if I plot this on here, we see that 1 1 would be this is, that is 1 1, that's the weight vector W, and let's say that the P2 would overlap on that, so P2 would be right on top of the one on the weight vector, but then we have P1, so this is 1 2 3 4, and this is 1. So let's say P1 is a vector somewhere here, P1 4 1. If we now try to project 1 1 onto W, it's going to be a small value. So if we as opposed to if we try to project this on that, so the length of projection of P1 on this W is going to be this big, right? And the projection of P2 on W would just be this much. And so does that mean that P2 is not less similar to W as P1? No, that's where the normalization part comes in. So if we have a vector which is, let's say, 4 1, if we calculate the length of this vector, the length of this vector would be just the square of 4 plus square of 1, sum of that, and square root, we get 17. Then what we need to do is normalize that projection. So cos theta with W, what we do is we take the dot product that's in the numerator, and then we normalize that with the magnitude. So we divide that dot product with the magnitude of each of those vectors. So magnitude of this vector for 1, which is p1, and the magnitude of the vector w, and that gets us a value. I've already calculated the 5 by 34, and that gets us value of 0.857. Again, here the W transpose P was simply 5. And if we now look at the point P2, which is 1, 1, if we take uh, the magnitude of that, we get value of 2. And if we try and find the cosine of this, this is going to be 1, 1 divided by square root of 2, square root of 2. This then becomes, this is essentially 2 divided by 2, and that gives us value of 1. Now notice that this is the normalized value, and these here are just the dot products. So yes, if we had looked at just the dot product of P1 with W, it has a larger projection. But if we want to compare just the how similar they are, we can also normalize them with these magnitudes, the length of their vectors, and so then we get a real picture as to how similar each of them are. So after we normalize, that is divide by the magnitudes of these vectors, we can clearly see that P2 has a larger magnitude, a larger value of 1 as compared to 0.85 for P1. And so this vector P2 is much closer to, or much similar to, the vector W. It's almost perfectly similar 1, because this P1 is sort of superimposed on that vector W, because they have the same coordinates 1, 1 and 1, 1. So that's all I wanted to say, is that this is the dot product, which is important in looking at similarity. It helps neural networks map patterns, and to look at the similarity, like the comparing similarity, we need to use the cosine. So we need to normalize the dot products with the magnitude of vectors to really compare them one on one. Right, so this was a long video. I hope this was helpful. If you have any questions, comments, or suggestions, please do let me know in the comment section below. I really like to hear from you as to how you find the series so far. Your feedback helps me improve the content and create new interesting content for you all. Thank you.